Hello everyone and welcome to this video on the fundamental theorems of linear circuits. The program of this video is as follows. We are going to illustrate some of the theorems you have seen in class. The reciprocity and integrand theorems will not be part of this video. However, you will then have the necessary tools if you want to study them by yourself. The first principle we have studied is the principle of superposition. This principle tells us that in a linear circuit, the current and voltage on an element of the circuit, resistors, capacitors, inductances, etc., can be given by the sum of the voltages and currents observed when each source is taken separately. We will see what this means on an example. I have prepared here a circuit that we will analyze. It is composed of a voltage source of 6 volts and a current source of 1 ampere. We are going to study what happens on the resistor R5. Note that I have not given a numerical value to R5, but I have named it RC. This RC is therefore between braces. I have indicated how we will use a dot step on the RC parameter. So this resistor will vary from 1 ohm to 15 ohms in 0.2 ohm increments when we run the .op command. To do the analysis of superposition, we will first consider the circuit with the contribution of the single voltage source. So here I have replaced the current source with an open circuit. Then I took the same circuit but studying the contribution of the current source. I then replaced the voltage source by a short circuit. I launched the simulation. Let's look at the voltage and current on resistor R5. Let's put the current in turquoise in order to see it well. I add a new table and I will display the sum of the voltages first. By adding the voltage generated by the voltage source and the voltage generated by the current source, we can see that we get the same overall voltage as below. We can see the same phenomenon with the current. I have summed the currents taken separately, and I also get the same result as in the original circuit. However, we will not obtain this result for the powers because the theorem does not apply to them. The goal here is to replace a complex circuit with resistors, voltage sources and current sources by a simpler dipole. Here a real voltage source. Idest an ideal voltage source with an internal resistance in series. The circuit we will analyze is the following. It is a circuit which is easily analyzable with Thevenin's method. The purpose here is to show you the tools of LTSpice. Therefore, use the procedure described in the course. First, we identify the terminals of the circuit and the external load. The load will be R5 and the terminals of the circuit will be here and there, so the terminals of the resistor. Then we have to measure the Thevenin's voltage. This voltage is the voltage at the terminals of the circuit without external load. We notice without doing the simulation that this voltage will be equal to 6 volts. Anyway, I launch the simulation and one observes indeed here a voltage of 6 volts. Finally, it is necessary to determine the resistance of Thevenin, thus this resistance here. For that, it is necessary to cancel the independent sources and to determine the resistance seen at the edge of the circuit. If one worked on paper, one would replace this source by a short circuit and this source by an open circuit, and thus again, quite easily, one would obtain that the resistance seen at the terminals would be equal to 4 ohms, thus to R4. However, what could have been done to measure this resistance if we had a more complicated circuit and wanted to use LTSpice? I have prepared this diagram to explain the method we will use. The idea is to replace this dipole here with this one. When we talk about replacement, it means that the dipoles act in an equivalent way. Previously, we have already calculated what the voltage of tefl was. We keep this result. Let's now determine this resistance with the LTSpice tools. We know that these two circuits are equivalent. On the equivalent circuit, we have that Vout equals V1 over 2, therefore equals 3 volts, when Ry equals R1. By this principle of equivalence, we will determine the internal resistance in this circuit. We are going to vary the external resistance, and when the voltage Vout is 3 volts, the resistance we will get here will be equal to Ry. We can also calculate the tefl's voltage by the same principle. Indeed, we must obtain the same voltage at the terminals of R5 on the left as at the terminals of R1 on the right. Let's start the simulation. As before, I use the function pointStep by varying RC between 1 and 15 ohms. I look at the voltage Vout at the output. I place a cursor and we will find out when I will get Vout equal 3 volts. We get that Vout is 3 volts when the resistance R5 is 4 ohms. From what has been seen before, this means that this 4 ohms resistance is the tefl's resistance. So we can build this equivalent circuit, thus an ideal voltage source of 6 volts and the tefl resistance of 4 ohms. We launch the simulation with the same options as in this circuit on the left. We can observe that the voltage is the same whatever the load resistance, which varies here. We can also observe the current on the external resistor, and we can see that these two dipoles seem to be equivalent. Norton's equivalence tells us that we can replace a complex circuit with resistors, voltage sources, current source, etc. by a simpler dipole, here a real current source, so with an ideal current source and an internal resistance in parallel. The procedure for Norton equivalence is as follows. For the first and the last step, it is the same as for the Thevenin equivalence. The difference lies in the way the current source is calculated. It is done by short-circuiting the terminals of the circuit and determining the current of the short circuit, which will be the Norton current. We take our previous circuit. I will skip the first and last steps that have already been done earlier. We are now going to determine the Norton current. In order to do this, we need to short-circuit the load. That's done. We are now going to calculate this short-circuit current. I would like to take the opportunity to make a comment about the measurement of the current. When calculating a current, pay attention here to the sign on the element, east to the direction of the arrow indicating the direction of the measured current. Here, we obtain that the Norton current is 1.5 ampere. So, we have the equivalent circuit of Norton with the Norton or Thevenin resistance, which is 4 ohms, that we have measured before, and here, the current source of 1.5 ampere. I take this opportunity to come back to the equivalence between our voltage source and our real current source. You saw in class that it was possible to obtain the equivalent circuit of Norton from that of Thevenin. The resistances are the same, simply of series, Ry become parallel. So both Ry are the same. The Norton current is also the Thevenin voltage divided by the internal resistance. So we have 6 divided by 4 and the result is 1.5. Of course, if I run the simulation of these two equivalent dipoles, we will obtain the same measurement. Here it is. You have seen that when we have a circuit where we can find the equivalent of Thevenin, the maximum power transfer is done at the moment when the resistance RL, the load, is equal to the internal resistance. We are going to observe this on the circuit we have just studied. We had seen that the internal resistance was equal to 4 ohms. I launch a simulation and we are going to observe the power dissipated on the external resistance, that is to say, the voltage multiplied by the current. We obtain this curve. It's a curve that looks indeed like this one. If I place a cursor, I notice that the maximum is about 4 ohms. This is the result we expected. I wanted to draw your attention now to the method to be used when one wants to apply Thevenin-Norton, but our circuit contains one or more dependent sources. The method is modified when one has to calculate the Thevenin resistance. A first method consists in cancelling the independent sources, putting at the terminals a voltage source US and calculating the current ES which enters the circuit. The Thevenin resistance will be Ri equal to US divided by Is. As the circuit is linear, the value of US has no importance. The circuit, which we will study here, is composed of an independent voltage source of 6 volts and a dependent current source. This current goes in this direction and is 3 times I through the resistance R2. If you wish to learn how to use the control sources, I invite you to go and see the video on control sources and quadrupoles, where we explain how to use this tool in LTSpice. Here, just remember that it is a controlled current source whose value is 3 times that of the current in the R2 resistor. I have drawn the circuit here again and I replaced the independent voltage source with a short circuit. At the input, I put a voltage source. So we will measure the voltage, so Vout, and divide it by the current in this input branch, so I in resistor R2. We obtain that the equivalent resistance of Thevenin is 4 ohms. There is a second method, which consists in calculating the Thevenin voltage at no load and then calculating the short circuit current. The equivalent Thevenin resistance is then Ri, which is equal to U0 over I0. To calculate the Thevenin voltage, the load must be replaced by an open circuit. I am not going to simulate this again because it has been done previously. We notice that it is worth 6 volts. On the other hand, we will simulate the short circuit current. So I replace the external load by a short circuit. I launch the simulation and I look at the value of the current. It is 1.5 amperes. If I divide 6 by 1.5, I get an equivalent internal resistance of 4 ohms again. I remove the short circuit. So we can replace our circuit with an equivalent circuit with a voltage source of 6 volts and an internal resistance of 4 ohms. I start the simulation and we will see what happens to the output voltage. We notice that these two circuits seem to be equivalent. Note that the method we had previously used with a variable resistor to find the internal resistance when the terminal voltage was half the terminal voltage would also work in this case with dependent sources. These theorems are also valid in the sinusoidal regime and with the related notions of impedance and phasor. Here are some examples. We are not going to go into detail because the procedures are essentially the same as those we have seen so far. Here, I have been able to replace this circuit with a sinusoidal voltage source by its equivalent dipole with a voltage source with an internal impedance in series. I can also replace it by another equivalent, a current source with an internal impedance in parallel. You can see that the same results are obtained for the output voltage in green and for the current in the external load in red. This video is coming to an end. Thank you for following it and see you soon for more videos.